Now we are going, which is our final case in this damping study. And case 4 is about over damping, where we consider that beta term is much, much greater than the spring constant term. And of course, if damping term is more, it's going to affect damping, and we basically have the over damping scenario. So this will be greater than omega naught square, okay? Or as we have seen, it would be like b square k m. Now here you see we're basically having the term in the numerator as beta square minus omega naught square. And as I said, in case of under damping, whichever is the larger term is taken first and the smaller term is taken later. In that case, omega naught square was greater than beta square, and then we have replaced it with a term. So here what we are going to do is, here beta square is greater. So what we are going to assume here is, there we use the term as omega 1. Let me use omega 2 here. In case 2, we have used omega 1. So omega 2 square is equal to beta omega naught square. And now we can do our replacements. So we can actually check this relation. And what was our expression here? Um, this was our expression, right? So we can take up this expression. Maybe we can copy it down there. Okay. And we can do our substitution. So this was our expression 2. And here, make it a bit more visible for you. So this was our expression, and here we are going to replace the terms, right? So here we are going to replace the terms. So this was omega naught square. So what you can say is, therefore, expression 2, it will signify x of 2 power minus beta t. Let's give a bracket. This is C1. And this entire term is omega 2 square. It's under root. So I can write it down as to the power omega 2 into t, plus I can write it down here as C2 e to the power minus omega 2 into t. So we have done our replacements. Let's see what else can be done. Let's just separate out and open the bracket. So in the first term would be nothing but C1 added. So what I can do is I can take the minus sign out. Inside bracket it would be beta minus omega 2 into t, right? These two terms. Then plus, again I can take C2, I can take e to the power minus, this would be beta plus t. We have, now you see both the terms are exponential in nature. There is no oscillating term, there is only the exponential term. So a very important conclusion can write here is, both are exponentially decay terms. So both are exponential decay term. Right? Both are exponential decay term. That will be decay term. Now, obviously, if I take it, this one I think I've written it wrong. Just write it correctly. This is beta plus omega 2 into t. Correct? Now there is beta plus omega 2 and beta minus omega 2, and it's quite obvious that this term beta plus omega 2 is going to be greater than beta minus omega 2. So that's important. So if you look into both these terms, so what we see here is that the second term is going to decay faster, right? It's quite obvious, because if the second term is larger and it has a minus sign. So, this is going to be at the denominator, and beta plus omega 2 is large. So that means, in simple words, beta plus omega 2 is large. That means 1 divided by e to the power beta plus, okay, is going to be a very small value because exponential to the power beta plus omega 2. This is going to definitely decay faster if we are comparing both these terms. You can do the math, right? So the conclusion would be second term is going to decay faster. That means the second term is going to approach zero. So the influential term would be the first term because this second term goes to zero for a larger time and when beta plus omega 2 is larger compared to beta minus means over a period of time we are only going to have the first term which is going to create the influence. So what you can say is therefore over a period of time, that's a very important statement that you need to put. We can have xt is equal to c1 to the power minus beta minus omega 2 into t. So for large time, the first term is going to create all the influence. Now, if you look into this expression, we can definitely say that there is no cos term or no sine term. That means there are no oscillations here, right? And of course, it's a case of over damping. So we call it as over damping. Now, it's very important, this is a case where you have an exponential decay. And if you go and check this case that we have here also, the first case rather, here also we have it, right? We do have, this is oscillation, the first term. The second term, we basically have an exponential decay, but also an oscillating term. But here we do have only an exponential term. There is no oscillating term. So what is the basic difference between the third case, where we are basically saying that beta square is equal to omega naught square? In the case is that of critical damping, and the fourth case, which is the case of overdamping. Both has got the exponential term. But if you look into it carefully, we can see that in overdamping, it basically takes more time to decay compared to critical damping. This will take a longer time for decay compared to critical damping because it's beta minus omega 2, but in this particular case, it's just beta t. So this value beta is larger compared to this. This is smaller value. Smaller value decay time would definitely be less. So you have to keep that in mind.